Hey everyone, we are working on problem number 3 from week 4. Let's see what the problem says. It says the value of G near the Earth's surface is 9.8 newtons per kilogram towards the Earth's center. Notice how G is a vector denoted by the arrow here, and because it's a vector, we are getting a magnitude with the units along with a direction. Always direction with vectors. On Mars, the value of G is a bit smaller, 3.7 newtons per kilogram towards Mars's center. When NASA weighed the Mars Curiosity rover before its launch, the reading on the scale was 8,810 newtons, 8,810 newtons. What would the scale read if we were able to weigh the rover on Mars? Now, weight, these are everyday common words, and something we've always been seeing in our physics class is that we as scientists don't always use words the exact same way that, the normals use. So we have a much more specific scientific way of talking, so it's worth talking about what weight actually means to us. Now, you'll see in a lot of books and a lot of people say, like, hey, the weight is the force that the planet exerts on the object. And that's fine. That's a good definition, too. Another way to think about it is also the force that the surface that you're standing on exerts on you, which, if you think back to the examples we did in class with elevators speeding up and slowing down, going upwards and speeding up, or going upwards and slowing down, we kind of talked about in class like how your feeling of weight sometimes goes up, sometimes goes down, but it's not that the force that the Earth exerts on you is actually changing. It's the force that the floor of the elevator is exerting on you that's changing. So, sure, we might define weight as the force that the planet exerts on you, but our everyday experienced feeling of weight is actually something different. It's the force that the surface is exerting on your feet on the bottom. So it's good to keep these in mind when we do problems that mix the scientific use of languages and the everyday use of language. But let's start. I don't know if you guys can hear it. There's a huge thunderstorm happening. Let's start with a sketch. So let me mark these off. Earth, our favorite blue planet. Let's draw that as a blue circle. So we have Earth over here, and what it's telling us is G near the surface of the Earth is 9.8 newtons per kilogram, and it points towards the center. That's what we mean by downwards, right? Towards the center of Earth. Mars, our favorite red planet, a little bit smaller, has a G value that is 3.7 newtons per kilogram. So for every kilogram of mass, it pulls it down with 3 newtons, pointing obviously towards the center again. Okay, in writing this, we're already running into an issue. We're using the same exact designation for 2 different vectors over here. Well, maybe I need to make my own modifications. I'm going to put a little E subscript over here, and I'm going to put a little M subscript for Mars over here. And when NASA weighed the Mars Curiosity rover, that's an SUV-sized robot, when NASA weighed the Mars Curiosity rover before its launch, so it was hanging out on Earth, and the Mars Curiosity rover has its feet and its eyes sticking out like that. Okay, that's tiny. I'm going to magnify this diagram over here. Here is the Mars Curiosity rover on a scale. And the scale reads 88 10 newtons. This is just like a scale that you had in lab that you saw, just a bigger version. So I'm just making a magnified version of that. And the question is, if we do the same thing on Mars, where the Curiosity rover is hanging out on Mars on a scale, and just to be fancy about it, I'm going to label my G weird. It's towards the center. That's perfectly fine, right? This is G equals to 3.7 newtons per kilogram. Doesn't always have to be on the top as we showed it on Earth. Same thing's happening over here. It is standing on a scale. What would the reading be over here? Okay, that's our sketch. What would the scale read if we were able to weigh the rover on Mars? Well, let's think about how we need to approach this. Well, this is clearly reading stuff in newtons. There's newtons per kilogram. A force diagram seems like the way to go. So let's draw a force diagram for when the rover is on Earth. My system is the rover. So my system is the rover. And what are the external objects that are interacting with the rover? External objects. Well, number one being the planet that it's near. So instead of doing two charts, I'm just going to say the number one is the planet, which can either be Earth or Mars, depending on the situation. And number two being the scale. The scale is touching the rover, so it's interacting with it. Okay, that informs us that our force diagram definitely needs to have only two arrows, not more, not less, just two vectors. So let's see. If I draw the first one, well, the scale is touching the rover from the bottom. This is the force that the scale exerts on the rover. And we are given a value for this, 8810 newtons. But I am not done. There is also the force that the planet is exerting on the rover. So the force that the Earth exerts on the rover. And something we saw in class is this can be computed, right? Like we can figure this out, the value of this. And that's given by the mass of the rover. I just introduced a new value. I should include that. Mass equal to m rover. So the mass of the rover times the vector g. Okay. Let's draw the same diagram whilst on Mars. Well, the surface of Mars, well, or the scale, I guess, exerts a force upward. The force that the scale on Mars, this one is the scale on Earth, the scale on Mars exerts on the rover is question mark. That's exactly what we're trying to find. And this is force scale on rover while on Mars. And there's another force. That is the force that Mars exerts on the rover. And we could figure this one out too, right? It would be the mass of the rover times the vector g, but now on Mars. So g Mars, g Earth. Distinguish between two different vectors if they're being designated by the same letter accidentally. Make sure you put subscripts or something to distinguish between them. Now, I already did something deliberate, right? I made the arrows a bit shorter while they are on Mars, and I'm kind of looking ahead in my head and knowing that when I compute this, the g value for Earth is a little bit bigger than the g value for Mars. With mass being the same, I know that arrow is a little bigger. So another thing we know is this: the sum of forces in this scenario is 0 because delta v is 0, or acceleration is 0. Same thing here. Sum of forces equal to 0. because delta V equal to 0. It's just standing still on the scale. Okay, from here, so from my force diagrams, since delta V equal to 0, the rover isn't moving or accelerating, sum of forces also has to be 0 in each case. From that, we see I could write two different equations. From that, we see for this first one, let me do that in blue. Sum of forces equals to 0. Put vector over here. We should choose a positive and a negative direction. Why not do the easy thing and call this positive y, and that's negative y. Okay, sum of forces equal to 0. So I get the force that the scale on Earth this force that the scale that exists on Earth exerts on the rover, plus the force that the Earth exerts on the rover has to sum up to be 0. Now, the force that the scale exerts on the rover, that gives me 8810 newtons plus m times g equal to 0. Now, which way is g? Well, in our case, g in both cases points downwards towards the center of the planet, so g is a negative number. So I get 8810 newtons plus m, and I get minus 9.8 newtons per kilogram equal to 0. That's my equation, and hey, this is already kind of indicating to us what we can do. So let me write this down as my explanation. I can already see there's only one unknown. From this, all of my sentences start with from. From this, we see it's easy. It's easy to figure out the mass of the rover. Well, let's do this. Mass of the rover is equal to minus 8810 newtons. I took the 8810 newtons on the right side. I'm doing a bit of algebra pretty fast here. Divided by minus 9.8 newtons per kilogram. Okay, let's see. The minuses cancel out, the newtons cancel out, there's a 1 over kilograms, and I get something that requires numbers to do, and I don't do numbers good. So let's see, calculator, 8810 divided by 9.8, 899.0, okay, 898.98. I'm going to keep extra numbers because I might end up using this. And what do I get left with? Kilograms. Okay, that's the mass of the rover. So we found the mass of the rover, but wait, that's not our question. We need to find what would the scale read if we were to weigh it on Mars? Now, let's do the same thing for Mars. Well, if I look at my force diagram, I see the same thing. Sum of forces equal to 0 since delta V equal to 0, which means the force that the scale that hangs out in Mars exerts on the rover plus the force that Mars itself exerts on the rover, all of that have to sum up to be 0, right? I just wrote this equation and I just spread it out over here. Now, what is the force that the scale exerts on the rover? Well, that's our magic number that we need to find out. So I will leave it as it is. Plus, I have the mass of the rover times g on Mars equal to 0. Notice everything is still vectors. Vector, vector. Okay. This one still stays over here as it is. Plus, now we have the mass, 898.98 kilogram. G on Mars has a value of 3.7 newtons per kilogram, but it is pointing downward, and we chose down as negative, minus 3.7 newtons per kilogram. Kilograms go away, and the whole thing is equal to 0. From here, I can see the force that the scale that's hanging out on Mars exerts on the rover is, I'm again going to do calculations while I do algebra, 898.98 times 3.7. Ooh, I get 3326. That's good enough. 3326, approximately 3326 newtons. The wiggly equals means approximately. Okay, hey, I have my answer. That's exactly what I was looking for. What would the scale read if we were able to weigh the rover on Mars? The scale on Mars would read this number. Okay, what next? We're not done. If you give me this, I'm going to take off a lot of points because we are physicists, not mathematicians. We don't care about numbers. We care about what the numbers mean. Are they okay? We like double checking ourselves. We always like thinking that we're wrong, and if we can figure out what mistake we made. So, evaluation. 1. Very easy. I expected the scale reading to be in newtons because it's a force, and I did get that. So that's part of my evaluation. Let's look at something else. I expected the scale reading to be positive according to my force diagrams. Because if you look at the force diagram, this is the thing we're trying to find, and it's pointing in the positive direction. This is the thing we're trying to find, and it's pointing in the positive direction. So, hey, did we get a positive number? Yeah, we had some negatives in our equation, but they all went away nicely, and our final thing came out positive. So I got that one too. Number 3. Well, G, the value of G, how many newtons the planet exerts on you for every kilogram that exists in your body, that value for Mars is about 3-ish, and for Earth is 9-ish, right? So, let's see. The value of G on Mars is about one-third the value of G on Earth. Therefore, I expect Mars to exert about 1/3 the force on an object of the same mass compared to the force that the Earth would exert on it, that the Earth would exert on it. Let me check that. The force that the Earth would exert on it over here is the same as this value, right? So 8810. And over here is the other value. mg on each planet, or let's make it nicer, the force that the planet exerts on the rover, if I just take the magnitude of that, is always equal to the magnitude of the force that the scale exerts on the rover. So if I take therefore a ratio of the scale, SCALE numbers, should be about 1/3. I do know the scale numbers now, right? 8810 and 3326. 3326 newtons divided by 8810 newtons is approximately equal to 3326 divided by 8810. And good enough. 0.377, which is almost 1/3. Close enough. I started everything with almost, so close. Okay. I got 3 different evaluations. Units, a direction from the force diagram that matches the math, so that's a consistency between 2 different representations, and some judgment call about the actual number relating to other stuff that we know. Okay, that's it. Have a good weekend.